Jacob, over to you.
Hi everyone, my name is Jacob Agboro, and like Femi rightly introduced, I'm also an associate at Amway.
Okay, thank you, Jacob. So once again, welcome to another webinar. Before we get started, I trust that in the past 2 weeks you've had a wonderful experience learning new things, learning about data science, learning about Python, learning about NumPy, different things. And I'm sure the experience so far has been nothing short of exciting. So today, before we start, I just want to hear your feedback on the experience so far, how the community of interns have helped you come this far into the internship, because I'm sure some of you have to learn something new, had to deal with a completely different environment. So I'll take 1 or 2 people from Zoom, and I'll take people also from YouTube. So people on YouTube, please type in your feedbacks under the comments pane, and then we'll get to you after addressing the Zoom feedbacks. Okay, so for Zoom feedback, please, if you have any feedback on your experience so far, please, by show of hands, just 2 people. Anyone? So nobody has any feedback on their experience so far. Okay, so I can see Damilola Laguju. Damilola Laguju, do you like to unmute and share your feedback with the rest of the house?
Hello, can you hear me?
Yes, I can.
Yeah. So the feedback has been great. The experience has been great so far. Doing the data analysis on the data sets and learning about NumPy and improving my Python skills as well. I think everything just ties into how great it's been, especially about data. You know, there's a lot you can do with it, and there's a lot you can draw from it that might not be quite visible in first glance. So yeah, it's been great.
Okay, thank you, Damilola. So anyone else? Just one more person. And I need you to tell me how the community has helped, how you've been able to network with other interns and leverage that to make your experience great. So just one more person.
Good afternoon. Can you hear me?
Yeah, I can. Good afternoon.
Yeah. So the experience has been awesome so far, and the community. So when I joined Amoye, I was confused on what to do, how to go about it, and then I met some people chatting on Slack, and hey man, what's up? What's going on? How can I do this? And then getting feedback from them. Okay, do this thing. This is where you have to start from. Send screenshots.
Hi, my name is Ezekiel. Can you hear me?
Sending screenshots and all that, and then that was actually awesome. The community has been helpful. For example, last night, I was trying to do something, and then I just messaged somebody on the community, and then I could easily do that. So the community has been helpful so far.
Okay, thank you very much.
You're on mute, Mr. Oluwafemi. You're on mute.
Okay, so very quickly, I'll just take a feedback from Mr. Oluwarotimi Arijeloye from Nigeria, connecting via YouTube. He says the experience has been great, though overwhelming, learning new things every day from fellow interns. I've been exploring the data sets too. Okay, thank you, Mr. Oluwarotimi. Lastly, I'll take Mr. Abdulrazak Ailokbedi from Nigeria also, connecting via YouTube. He says, it's been a good experience and I'm still looking forward to taking the assessment. Thank you. So I said I should have taken the assessment by now, but thank you for looking forward to it. Okay, so at this point, I'll hand over to Tobiloba Adejumo, and I wish everybody a great webinar. So listen and stay plugged in. Thank you very much, everyone.
Thank you, Femi. Hello, good afternoon, everyone. I'm so definitely excited to welcome you all to today's webinar. How many people are already online? I can see a couple of people already on YouTube. I can see people also on Zoom. I think probably I should spend 2 to 3 minutes before time to actually talk about some of the things that Amoye offers and also to welcome you properly. And I'm delighted to have you on board. You can use the live chats on YouTube to let me know how you feel this afternoon. Currently in Lagos, it's sunny, and on YouTube currently, I have to appreciate Ezekiel Ibe. He was the first intern to join YouTube. And Isabel Ibe, thank you very much. Tomi Arotiba, good afternoon to you too. Kola Deawu Olawoyin, good afternoon. Kola De, thank you for coming on board today. Now, quickly, just a little housekeeping rules before we start. If you have any questions, any linguistic propositions, uncertainty, doubt, trouble, or anything at all that you're not really clear of, you can wait till the end of the session we'll be having today and post in your questions on Slido using the event code 20340. Again, use Slido. The event code for today's meeting webinar is 20340. Now, without further ado, I'd like to turn the table over to our country manager, Shola Olateju. So Shola has some few words to say today to all of you, carefully and meticulously baked words for you today. So Shola, over to you.
Hi, everyone. It's good to have everyone join again. Welcome to yet another session. For me, I always look forward to Saturdays now. I learn a lot from this interaction as well, and seeing all the connections and the conversations on Slack, and the experience we're all having learning basically has been nothing short of awesome. So we thought about what are the ways we can further enrich this experience, and we, as a data professional, like some of you have identified, there's so much that is possible and so much that you can do. But we thought there's some peculiar problems that you might run into during this journey. And one of it is having to do with the duplicated data. And by duplicated data, it's more having to identify unique users from multiple data sets. It's one that I would expect that at one point or the other during this journey, you will have to deal with, and it's the reason we're doing what we're doing today. Today we have someone who is going to be sharing from his wealth of experience, and we're going to take time to explore how to identify profiles that belongs to the same user or entity, but then from multiple data sources. Charles, again, as we all met him, connected with us earlier on. We are excited to have him join.
You're on mute, Amoye. The speaker is on mute.
Sorry, Shola, you're on mute.
Oh, really? So sorry about that. Thanks once again. Was I on mute from the beginning, Femi? Was I muted from the beginning?
No. 10 seconds.
Okay, that's fine. Okay, so without much ado, I'm going to hand over to Charles now. We all know Charles already. He was with us 2 weeks ago. He's a big friend of the house and a partner, and we're always excited to have him share from his wealth of experience. Thank you for joining us again, Charles. I'll hand the mic over to you now. Thank you.
Yeah, sure. Good morning. Can everybody hear me properly?
Yes, we can. Yes,
all right, cool. Yeah, I didn't know I was going to be back so soon, but I mean, I'm really excited, and good day to everybody wherever you are. Good morning, Lagos, Accra, Addis Ababa, Nairobi, South Africa, and everybody joining us today. Thanks for joining us, and I'm going to be talking about one of the presentations I did at a conference earlier this year that shows our application of big data how we apply machine learning to a big data problem. And it's a good use case. You guys will probably encounter it at one point in your career where you want to solve problems, and this will walk you through the technical step. It might be a little bit overwhelming, but I'll say just try to understand the concepts. At some point in the future, you'll probably be able to connect the dots and see how this will be relevant to what we're trying to do. So to get started, I know there will be a lot of questions on the other side. I will just share my screen, and I like to just tee up things with videos, just like break the ice. So I'm going to just play a YouTube video from the NVIDIA GPU conference in 2019. Then on the other side of it, I'll take it off with my slide and my presentation. I'm going to try to share my screen now. Can you all see my screen?
Not yet. Yes, we can. It's coming up.
What about the audio?
No, audio is not out here. Perfect. Audio is good.
I am a visionary, bringing characters to life with more natural movement, generating brilliant new worlds for them to explore, and inventing new ways to bring out the creative genius in us all. I am a protector, leading the way into the most dangerous environments and searching for signs of life. I am a guardian, listening for the sounds of destruction to save our forests, and using satellites to bring freedom to those who are enslaved. I am a navigator, finding safer paths for cross-country deliveries and taking personal travel to new heights. I am a scientist, exploring oceans of data to understand extreme weather patterns and studying the building blocks of life to save a community from hunger. I am a healer, giving hope to those who suffer from the most challenging diseases. And tapping into the brain to rejuvenate paralyzed limbs. I am even the composer of the music you're hearing. I am AI, brought to life by NVIDIA, deep learning, and brilliant minds everywhere.
Cool. That was from the NVIDIA GPU conference. And it's interesting. There's a lot of problems to solve. There are very few people to solve it. And that's why we need you, and that's why we need everyone to be involved in this and be ready to learn and participate and things like that. So to get started, I'm going to be talking today about one of the use cases and one of the problems that we're trying to solve with AI and ML. It's a massive big data problem. So the problem, just for me to explain it, again, is let's imagine you have a large data set, and that large data set contains people's names. So, and it happens all the time where you use your first name and your last name, or you use your first name, middle name, and your last name. And all those entries get inside the database. Now, imagine you have 100 million records. Imagine you have 1 billion records. One thing that we can do as human beings is like, if I see you, your name is John Smith, you're born in 2010, and your name is John A. Smith, and you're born in 2010, maybe January, and the other record is November. I can quickly infer as a human that, okay, it's still the same guy. It's just that the record was like mixed up and stuff like that. And it happens a lot where you have all these data sets with like duplicate entries, and the computer thinks it's still a different person, but in reality, it's still the same profile. So what we try to do was to basically use something called Bayesian generative models to understand the intrinsic properties of all these attributes and be able to like infer with the AI or ML that this guy, even though the records are different, it's still likely going to be the same person. So that was a problem we solved with these, and I'm going to just walk through the slide and just talk quickly through it. And on the other side, you can ask me questions. You guys probably know me. I work for Maven Code. We're based out of Dallas. We do a lot of things around AI, ML, and some of the things we do is like we process large scale, we build large scale data pipelines and cloud infrastructure. So a lot of all the things we do it with our service partners in the cloud. We're partners with Amazon, Google, Microsoft, Azure, all in the cloud, and we help our clients in developing all these kind of solutions. This slide was presented by my colleague and I, Timo Mekler, at the Databricks Spark AI Summit. So it's just a rerun of that. So if you want to follow us on Twitter, that's a profile. So like I said earlier, the goal is to be able to like identify profiles that are occurring in multiple places, but in reality, they're still the same person, probably because a slight delta or a slight change in their attributes. So this is a typical example. So let's say James Doe Smith, born on 11/01/2000, lives on this street. And you have another James D. Smith, born on this date, lives in this street. And you have this James Doe Smith, born on this date, lives in this street. Apparently, it looks like all these James Doe Smith, they're still the same person. But just imagine you have 1 billion records of different people in your database and you have all these multiple entries. It's difficult for you to like point out that, okay, James Doe Smith and this James D. Smith, they're still the same person. SQL query will not do it for you because you want to do it for all the users in your database. So we needed a way to like dedupe and understand all these things. So that's the problem we try to solve here. So why do we have data duplication problems? Sometimes it's due to like incomplete attributes or missing attributes. So a field might be missing or someone made a mistake while they put it in the field. Data coming in from different sources. Some data are spatio-temporal. What I mean by that is like the data basically, like let's say your cell phone data, you travel to somewhere, you join the Wi-Fi, and during that time they get your records and everything. So your record exists in that location, but it might not be there for a long time. And you might have traveled to the same location multiple times, and you join the Wi-Fi and you're changing your phones and stuff like that. And for the most part, unavoidable human errors. So where do we see these problems? I mean, what the duplication challenges becomes more complex as your record set grows. So let's say you have 1 billion users, which is a kind of problem people at Twitter or Facebook have. How do you identify duplicate fake profiles so that you can remove it? And sometimes it's due to like a lot of companies merging together. They have all these legacy and modern systems and you're trying to synchronize it. And it happens if you're building a big web application where people sign in multiple times with different profile and you want to like identify the duplicate records. So where do we see these problems? We see it in travel and hospitality, where if you're traveling, they have your record. Let's say you travel, you're traveling for a vacation, you fly down to a location, you booked your hotel with a different name. You got there and your ID card shows your middle name and your last name. And they need to be able to reconcile that, okay, this same guy that booked a flight and reserved the hotel is still the same person. Insurance claims, which is like, it's a very big deal where people want to claim damages from their insurance, but the profile's a little bit different, but it's still the same person, or maybe not the same person. You want to be able to like identify that and eliminate any kind of fraud. A big deal out here is medical and healthcare, where if I go to the hospital, let's say I'm in Texas, I go to the hospital in Texas, my name, my first name and last name is on paper, but I travel to another state and I go to the same hospital, a branch out there, and at that point, maybe I used my middle name or my first name, middle name, and last name, then there might be disparity in the records and stuff like that. And of course, social media, you guys do it a lot. A lot of our, I mean, virtually all of us out there are probably on LinkedIn, Twitter, or Facebook. So you have social media marketing where you have records and feeds coming in, and you want to determine if this user is still the same person that logged in on Facebook. Is it still the same person that logged in on Twitter? Is it the same person that logged in on LinkedIn, so that you can have a 360-degree view of your customer? And of course, during mergers and acquisitions, when companies acquire another company, they are bringing all these data sets, and you want to make sure everything is on match. And one of the most important part is the fraud and digital trail. A lot of people doing crazy things online think they're invisible, but the fact that you can basically identify their profile and track their IP and be able to like build a record around them, so that you can know like, okay, the guy that came in here is still the guy that appeared there and everything. So you can build a triangle that basically identifies and box up the kind of individuals doing all those crazy stuff. And of course, one of the interesting use cases that we're looking at right now is in community health, where you want to be able to like trace people that have COVID. So if someone has COVID and gets in contact with multiple people, you want to know like, okay, is this the same guy that traveled to Lagos that actually went to London and Amsterdam? And you can basically trace and identify and see if it's still the same person. So on a high level, this is how the problem is. There are different ways of solving it. People sometimes try to compare things element by element, but just imagine you have 1 billion records and you're trying to compare each element. It becomes very difficult and very complex. So that is not scalable. That won't work. So we need to find a smarter way to do it. The other thing is like using logistic regressions, where you have some attributes and you try to like do it with like label data, so that you can predict based on all the categorical classifications and stuff like that. Again, I mean, it's a very common solution out there right now. It's easy to implement, but it requires a lot of labeling, and it's not really very efficient when you're dealing with things at scale. Then the other approach, which is a lot more probabilistic, is a naive-based approach, where you try to like associate attributes, a similarity measure to the attributes, so that you can compare how the attributes are close enough. So there are different similarity measures. The distance, basically, you want to be able to like vectorize the name and properties and see how things are connected and see what's close and what's far apart. And based on that, you can create a cluster and things like that, which is what we're looking at in this problem. And this is basically one of the other approach using unsupervised k-means clustering and things like that. So again, it's heavily dependent on what centers you choose, because you're trying to cluster the results around certain attributes. So you might take someone's last name and try to find everybody with the same last name and try to like see, okay, everybody with this last name, are they all the same people? Do they belong to the same family? Do they belong to the same group? And things like that. So, so the current solution is one of the things you do a lot. Is like you have something called the blocking attribute, which basically you use to like categorize things, because if you're dealing with like large scale data sets with like billions of records, it's not really efficient to like start comparing things one by one all through the billion data sets. So one of the smart ways people devise is to come, one of the smart approaches that people have devised is to come up with a blocking technique that basically allows you to like put things into different blocks or categories. And you need to devise your blocking technique so that it's very efficient, and it allows you to like just group things that are likely going to be the same inside the same box. So let's say I'm trying to search for people with like matching names and matching properties, and they live in like in this case you can block by gender, but that's not really going to help because you have male or female, which is binary. So you need to think about your blocking attributes. It should be something that can easily create a block of people or attributes or entities with the same attributes in the same bucket. So let's say I want to block by people traveling around and stuff like that. I can block by your city. So if someone is in Lagos, London, New York, they can fall in the same bucket. I can easily process those buckets in silos and without worrying about the other buckets and things like that. So that allows you to like efficiently partition your data and be able to like utilize all these things on a distributed compute like Apache Spark, which I'm going to talk about shortly. So I talked about how you compare things. Basically, you want to know the distance between two things. So which is like you're trying to represent distance as vectors. So the normal understanding is like if I want to see how two things are, how close two things are, you measure the distance. If I want to know if you're living close to me, I try to find where do you live, and once I know where you live, then I can find the distance between our different locations and be able to say, okay, you live like 10 miles away from me, 1 mile away from me, or you live next door, and that tells a lot about how close we are in terms of proximity. That's the physical distance. So you can do the same thing with like names as well, which is the different techniques where I can know like the name of this guy is still the same guy. It's even if there's a typo, or even if the name is like an abbreviation or things like that. So it's called distance measure, and that's how you measure the similarity between two things. The distance apart. So the vectorial representation of the distance apart. So the different approaches, Levenstein distance. So it basically measures like the number of single character edits required to change a string from A to B. So like John and John, the Levenstein distance is 1 because you just need to change one of the letters and it becomes the other one. And John and Jack, the Levenstein distance is 3. So this is a lot more closer than this. So if someone is John and in the database they represent him as John, it's likely going to be a typo, and it's probably the problem in John. So the Levenstein distance is 1, whereas the chances of calling John Jack is very low. So that's the Levenstein approach, and we have a combination of this approach that we apply all to the attributes and stuff like that. And same thing with like different representation of things, Jarrow-Winkler distance measure, and the phonetic comparison, like someone called Ashley and Ashley, or Lee and Lee. They sound alike phonetically, so they might be close. So maybe when you got to the front desk, you say your name is Lee, and so and the front desk guy had Lee, and they punch this into the records, and that's how all these problems arise in the first instance. So the whole goal is to be able to understand the similarities and the distance measure between all these attributes, and be able to like use them to calculate how similar the attributes are for a particular person to like another person, and that way you can know, okay, if someone is being called Lee or Lee, it's basically a matter of the phonetics, and that's why there was a mistake in the first place, and it's likely going to be the same person. So our approach, like I've been saying, is like it's completely unsupervised. So using the Bayesian generative technique, the model tries to go through the data sets to understand what's going on. And it's able to basically identify the patterns that we talked about and be able to like cluster similar record sets together. And there's a lot of uncertainties between two stages where once you partition the data into blocks, you might have the wrong data sets in the wrong block. So we basically we're able to like move things around across our distributed clusters where all this processing takes place and things like that. So this involves a lot of things. So I'm going to be talking through this for those who are like on the data engineering track and interested in all these kind of things as well. So data preparation is like the data comes from different sources. So we need to like prepare the data sets. Basically have a schema that defines the input, the first name, last name, date of birth, address, and all the attributes. And we now need to chunk it and slice it up because we're using Apache Spark, which is something that you guys need to check out. Basically, we can chunk out the data sets into like different subsets and push it to different compute nodes. And everything computes in parallel. And that's how we get our end results and things like that. So on a high level, that's the infrastructure pipeline, which I'm going to be talking about more in detail as well. So the description of the approach is like you have all these records. So let's say we take a subset of data. We have the entity. We extract the records that represent the entity. And basically, we assume that the records are distorted, which is like they're not like the true representation of what they say they are. And we try to cluster the records that are similar. The profiles are similar inside the same bucket. And if the record doesn't get clustered after multiple iterations, because we check the bucket, we do like subsampling to like check the bucket multiple times. Like, does this John Smith as a matching record in this bucket, in this partition? If it doesn't, then we move it to another partition, we compare, and we keep moving it around and stuff like that. So there's a lot of shuffling between all the nodes in the distributed cluster. And we keep doing that iteratively, multiple times until there's a convergence and we think we have something close to the right answer. So we do that over and over, pushing the records across all these buckets and as things go on. So on a high level, that's the design approach. And a lot of credit goes to the guys that, well, what we did was based on the conference paper, the DBLN guys, distributed end-to-end Bayesian entity resolution by Neil Marchant. So they did a lot of work on this. So a lot of other things we did on this project was mainly based on their research work and their prior knowledge in this domain. So for us to do this, we need to think about these things as a probabilistic entity model, which is you think about everything as for those of you doing physics, kind of like particle physics. So you want to represent entities with with profiles, and each profile has a probability distribution that represents a kind of certainty that there's a matching pair within your billions over a billion records in data sets. So the whole idea is for us to be able to like identify things that are close enough and be able to like push them together and things like that. So for us to do that, we have the entity representation that will assume like every entity. And in this case, we're talking about human records. In some cases, it could be digital trail. So I want to know people coming to a website. I want to know their attributes. And based on their attribute, I can basically infer that, okay, even if you're coming from this IP and this IP, what you're doing tells me that you guys are still the same set of people. So we can do that with user profiles as well. And the other thing we do is to like partition the data sets, like I said earlier. So you want to partition the data set so that we're using a distributed cluster so that you can push each partition to a node in your distributed cluster. So that allows you to like compute things at scale and do things a lot more efficiently. And we assume that these attributes, there's likely distortion, which is non-conformal. What that means is like you have an attribute A and attribute maybe B. A and B may be still be, entities with attributes A and B who may still be the same user or the same profile. But the fact that there might be a similarity between them, we don't know, but that's our general assumption. And basically, we extract the records out of the profile. So all your attributes create a profile for you, and that's what gets attached to your entity. So in that case, let's say you're like, let's take a person, for instance. Your profiles may be your date of birth, your name, your first name, last name, age, sex, address, and things like that. So those things are called, those are the attributes that define you. So you extract it, and that defines your profile, and that's what we're comparing. So this entity with this profile that has these attributes, we want to compare the attributes in your profile and see if it matches any other person's profile, which is the logical way, the way we think as human beings. Like once I see your last name and your address, I can know if you have a brother or if you're related to someone and things like that. That's what we're trying to train the AI model to be able to understand that skill. So the thing about us as humans is like I can do that for a few people, which based on my address, based on where I live and my knowledge, I can know if two people are related or they come from the same place. But and my knowledge is localized to what I know. But what we're trying to train the AI model to understand is basically study all these relationships and be able to like infer these things as skills, so that if you're like an Asian from China, the model can understand if you're German, if you're like Israeli, and things like that. So it goes beyond just what I can understand as a person and deal with the data locally in a particular region. It tries to understand all these things and be able to like build a graph or a mental model of what the relationship are, and that's how this will work at scale. So this is an implementation pipeline again. These are like, let's assume like these are your data sets. If you're talking about social media data, so let's say this data is coming from like all different data sources. Let's say LinkedIn, Facebook, Twitter. And you want to know like, okay, if is the same guy posting on Instagram that is on Twitter, that is on LinkedIn, or is it someone else? So we're bringing all this data. We create a general schema, and we basically union this and put them in that schema. So we have like huge, massive piles of data sets. So we use a language called Scala. So for those of you wondering what this is, it's Scala, where you say like, okay, I have these data sets. I want to like combine everything together. So we're trying to union the data sets and combine it into like a bigger data sets and things like that. Then we push it out to like, I talked about Spark, which it's like a framework that allows you to do distributed computing at scale. So all these nodes are connected together in a cluster. So we push all these data sets. We basically splice the data sets. So there's something called the partition function, which is it's a partial function that allows you to distribute your data almost evenly. You can't have it 100% even, but let's say you have 100 billion data sets. If you choose your partition function right and you specify the number of partitions you want, it's going to allow you to slice up the data into like different chunks, and you push all these chunks into all the different nodes, and that's where you execute and do the comparison. And if something doesn't belong to a particular node, it's going to get pushed to the other node until it finds its matching pair, and the whole process continues iteratively over and over. So so let me just talk briefly about the Bayesian generative model. I'm not going to go too deep, probably because of our time, but I'll tell you a little bit about it, and you can go do some research, and you can follow up with me as well for those who are interested in this. So the Bayesian approach, and it's from a guy called Bayes that lived a long time ago. And what the whole approach is all about is like, if you observe something over and over, you can basically be able to like predict any future kind of behavior by all the prior observed behavior. You can predict what's going to happen in future. So let's say every time there it rains continuously for 5 days, there's going to be a flood. So naturally, that's the way we think. So if it rains continuously for 5 days and there's going to be a flood, then you can say that every time it rains at 5 p.m., there's going to be a traffic jam. So that's the way we reason as humans. And because how do you know that? It's because you've observed it over and over, and you can infer this basically. So that's the naive Bayes approach of thinking about all these things. So if I know a lot of power information about you, and over I've observed it, then I can predict what you're likely going to do in future. So let's use this case. So my name is Charles, and some people call me Charlie, and my Timo and I work together. So this is called, you can see the transition. So like most people, it's very low. So this is a probability distribution. So over time, if you observe, like every time people try to react and relate to me, there's a low probability that people will call me Timo. And there's a low probability that people will call Timo Charles, but there's a high probability that people will keep calling me Charles. So this is like 7 in 10 times people who know me as Charles will call me as Charles. But people also call me Charlie, some people that are close to me. So there's like over time, maybe like almost 20% chance that people who call me Charles will call me Charlie. And people who call me Charlie, there's 34% chance they will call me Charles. So there's a like observation that I mean, over time, we've built up, and I can know if someone is calling me Charlie, it's probably someone who knew me and calls me Charles as well. So that's the observation. So with that, you can build a big matrix, and that basically represent this, and that's what we're trying to do. Like, okay, is Charles still the same person as Charlie? There's a strong indicator for that, but is Charles still the same person as Timo? There's a low indication for that, but sometimes people may mistake Charlie for Timo, and there's a probability that I'll be called Timo. So that's the problem we're trying to solve with these, and that's the naive Bayes approach, and it's natural. That's the way they're remembering things, because if I've observed things over and over, that's how you react, and maybe some people like to call it experience. So you react based on your prior experience and what you've observed before and what you've seen before. So you can see the strong correlation, like just because the people calling me, some people call me Charlie, so that's the probability distribution. It's a little bit low, so it creates a drag on people that call me Charles, but because people will call Timo will most of the time call him Timo, so there's a strong correlation in that. So so that's what you see out there. So and if you want to ask me any other question on the other side, you can ask me as well. So this is I'm just going to blow this up a little bit. So this is a partition partial function, which is a partial function is a way, for those of you with maths and physics background, is like the way you basically break things apart based on a particular attributes that basically allows you like categorize things, or basically allows some things to go through a bucket, and it won't allow the other things to go through because they don't belong to that group. So we use something called the KD tree partitioning, which you can look it up as well if you want to talk a little bit more about it, but I won't go too much into details, just like generalize. But the whole idea of the KD tree partition is like you can develop like a hyperplane that separates your data into different categories and different buckets based on the attributes that you define in your partial function. And you specify the number of partitions, and you specify how many records you want to fit in that partition, and you give it a unique ID. So inside that bucket. So let's say I have like a 10 node cluster. In this case, I've used a 4 node cluster. I want to divide my record set into different partitions, and I want to partition it based on maybe their last name or their city. So the data will come in through this place, we'll split it up, and you can have the partition, and that partition gets shoved into the cluster out there. Right there. So let me see here. So so just to show you how this works in practice. So you have, let's say you now have like all the 4 nodes after shuffling the data. You have like three attributes, 5 attributes, 4 attributes out there. So once you shovel the data, let's say we look into this one. This is a very interesting, in the first node in our cluster. So this is a cluster of computers talking to each other, and you have all these nodes in them. So let's say you have these nodes with this 3 attribute. Let's examine this node. You have all these 3 attributes in that node. And let's blow it up a little bit. And let's say this is a profile that we have in that node. We have Rob Jones, born in 1991, living in Salt Lake, Texas. We have Bob Jones, born on this date, also living in Dallas. And we have the same, almost similar attribute because they've been clustered together based on our partition function. So we're looking at these records and everything. Rob John Jones, born in 1992. It lives in Dallas, Texas. So for those of you who are familiar or not familiar with it, Dallas and Salt Lake, they're almost the same area. I live close to this place, so that's why I'm using it as an example. So basically, the records look almost identical. Dallas from Salt Lake is probably like a 20 minutes drive, and the profiles almost look identical as well. So let's examine that. So to make it a lot more visual, we've been talking about entities and profiles. So I extract the records out. Like this is the entity, which is a person, and I extract the records out. Basically, that's what we're doing. And we do a similarity measure of the distance between all these attributes. So Rob and Bob, if you calculate the Levenstein distance, it's almost the same thing. So from what I showed earlier, the Levenstein distance, we showed this as 1, because you just only need to change one word to be able to like match these two together. So it's a strong similarity. If it was Rob and James, it's probably, the distance will probably be about 5 or something like that. So, but the distance is very close. So it's probably the same person. Same thing with these attributes. These attributes, John and John's, it's almost similar. So there's a strong correlation. The date of birth, it's almost close as well. And the gender, even though it's missing out there, we can see the strong correlation between all these attributes. So basically, that's how we measure the closeness and determine that, okay, this record belongs to this cluster. And if it doesn't belong and we think we can't cluster all these attributes together, we broadcast it to another node. So it's called, there's a way to like push the attribute to another node. And you go through this iteration all over again until that particular profile or entity gets a matching profile in the distributed cluster. It will keep bouncing around and around and around all the way through and stuff like that. A little bit of recap. All these things, the similarity measures, I think I talked about it earlier. We use Levenstein, Zero-Winkler, JCAD. You can read up around this as well. I don't want to like bore you too much about all this concept, but it's something you can pick up and just understand how all this working out. Everything ties together. So yeah. So someone is messing with my screen. Yeah, if you can clean that up. So yeah. So those are what we did. So I'm just going to show a quick demo that talks through all these things, just to put a lot more light into it for those of you that are interested in this, especially those who will be doing things around data engineering and pipelining, just to understand how this works. So I have this. I'm going to play it real quick. So Google has a platform called the Dataproc, which is like a cluster that allows you to like build a node where you can run all these things at scale. So we're using the Dataproc cluster on Google Cloud. So I connected to the cluster. I ran the Spark. It's very easy. So it brings out the Spark prompt. So you guys can look up Apache Spark. Is a way to connect gang all these computers together and distribute all your data sets across them and process things in parallel. So it's gonna take a little while. So basically what I'm doing is like, I'm trying to like load up the data. I'm trying to load up the data sets. So this is a data set that we're loading up. What I've done is like, I have them in the common schema. And I loaded up the data sets. Like this data set is actually from a city in Australia. I mean, it's from Australia, so you can see the postcode. So like the names and address, what we're trying to get at is like there's some duplicate profiles out there, and we want to identify these duplicate profiles and be able to like use our algorithm to determine if it's for the same person or not. So these are like is it states in Australia. Yeah, so these are like the way they're represented. That's a short form. So Southern Australia, I think. Yeah, Victoria. Yeah, and things like that. So that's the data sets. I just loaded these up, and these are like the addresses, the first name, last name, and yeah. So yeah, that's the way we have it. So one thing I try to do is to like also like all the dates, and if I'm dealing with date, I try to like strip out like the hyphens or the dash. Same thing with the zip code, because you want to measure distance between date of batch, you want to make it easily for the algorithm to calculate that at scale and stuff like that. So we do that a lot. So yeah, so these are like all the records and all the attributes. So let me move a little bit more faster. So once we do that, we load it up. Once we load it up, we load it up into like the Spark job, basically loads up the attribute, loads up the data sets, and we run it through the naive Bayes model that basically calculates the similarities between the data sets. So it takes some time. So we didn't load up a big record data set because we wanted to show, we're showing this at the conference. So we didn't want something that would take hours or things to complete. So it's just, so these are like the record sets. We basically index all the attributes to see how unique they are. So the first name you can see, like there are 2595 unique values. The last name has 5193 unique values, which it kind of makes sense because most people have the same first name, but your last name to some extent is sometimes unique. There's more uniqueness to the last name than the first name. The date of birth, we have different values. Again, that makes a lot of sense, over 10,000. The street numbers, it makes sense. You have low number of street numbers because it's more likely most people live on the same street, in the same address of their families and stuff like that. So we index the data, and once we do that, we'll run the training. And once it's done, it's going to drop the data sets into a data storage on Google Cloud. So we created a bucket for that, where we run it and we get the results, and we push it to the bucket. Oh, sorry. I think I messed with the video. Yeah, so let me see. I'm gonna. Okay, so that's when the data set gets evaluated, and you have all the things you want to do. So the bucket is like a storage location where you dump all these things. So the different diagnostics and the results, we run it through like the Markov chain Monte Carlo simulation. You do a lot of self-samplings and mappings and stuff like that. So I kept talking about like how the data sets comes in and stays in these things, in these clusters, in different partitions. So let me just see if I can show you that for a second. So you can see like all the partitions. Yeah, so you can see like we calculate, we have like a bunch of nodes in the cluster. So each data set comes from each partition. That's why you have part 1, part 2, part 3. All the data set, once they're done, the result gets aggregated, and you can now pick it up and do stuff with it. So I just wanted to point that out real quick. So once the results is done, one thing I try to do is to like load the results. So let's see the results in that yeah, good. Yeah, so that's it. So you can see like each record has an ID. So what we've done is like we clustered the attributes or entities that we see that have the same ID on the same line. So you can see all the attributes. So these are like all the attributes. All these things are similar, so that's why they're on the same line. That's a unique ID. So what I'm going to do is to like pick that unique ID and basically try to look at the attributes in the data set. So we're going to see that shortly. So we'll take all those IDs and we'll try to look up the values and see why the model thought they were like similar and why they got clustered together and why the ML model was able to like predict that they're almost the same thing. So you can see that. So those are like the list of the attributes. So I basically took all the records IDs for the similar attributes. Then I go back to my data sets, and I'll try to like import and read all the records for that attributes that I think were very similar. There you go. So so these are like okay, so that's the big data sets. Then the next thing we're gonna do, so this is just the dedupe data that we're deduping. So I wanna like just subset and select these attributes, the IDs and everything that we picked up that we thought maybe they're for the same person. So just give it a minute. Let's get there. Let me just, I'm gonna play it fast so that we can. Okay, so we take that attribute. Move it fast. Okay, so sorry, I had to like move it a little bit fast because we're running out of time. So I can just pause it here. So you can see like the first name is Aaron, the last name is Humphreys. The date of birth is this, the street number is this, the street address is this. Oh, this address is different. Stonehaven Crescent, all the addresses almost match except this. Then we have like empty record data sets here. We have the postcodes are similar. The state code is similar. The record ID, which shows the uniqueness, is different. So imagine you're trying to sort through a pile and identify someone with this kind of attributes and identify that it's still the same person and you have a billion record. That's going to be like a huge task and something very difficult to do. But with the naive-based approach and what we've done, we can basically identify similar attributes and group them together and basically tell a human person or someone at the front desk that, okay, even though you're looking at this person, it's technically still the same profile. And that's how you solve all this problem with skill. It's a very interesting problem, especially like when you're dealing with like large, massive data sets and things like that. So that's what we basically solved in this. I think, okay, there's one more record that we can look at and we can wrap this up. Okay, so this is another record. In this case, the first names are missing, but you can see the last name. So probably someone was just messing around, trying to sign up multiple times and stuff like that. Kidzoy, Kidsley. Sometimes the last names are empty. Then this is the address. This is the location. Even though there's typo with things like Levenstein, you can easily pick that up and in fact that it's still the same person. So the model can pick that up and identify that, okay, this is the same person and that's a profile and that's it. So that's a problem we try to solve with skill, and there's a lot of applications to this, and it's a very interesting problem. We're still exploring it as well. We're doing a lot of research in this area and trying to understand all these things ourselves. So I look forward to like talking to people who are interested in this and will want to like do stuff with us. I think that's it. So why Spark? It's a common project in the open source community. It's it's batch tested. It's a framework that we use just a lot, so it's easily scalable. So I can add more nodes and do a lot more computations as I need, and we basically leverage what's in the cloud. So we pay per usage, which is like if you're very smart about now you use a cluster, it's not very expensive to do. So in summary, basically we've used a Bayesian generative model for data linkage and deduplicating. We want to identify duplicates and do all the record linkage. We partition their data sets and leverage Spark, which is a distributed computing platform. So it was easier for us to like just do a lot of things off the bat and leverage on the Spark framework. We can do fuzzy inexact matches where things are not like almost similar or some things are missing. But by doing some distance comparison or similarity measures, we're able to like identify all these things and know like, okay, these guys are similar. It's almost the same thing and stuff like that. So, and the level of accuracy is acceptable, even though it's unsupervised. So normally when you want to do these things, you bring in domain expert or someone that understands understands that domain and stuff like that to be able to do this. So that's called supervised learning, where you label things so that if you see somebody with this last name, put them in the same bucket. And that's what they call experience, where someone sits down, they spend like maybe 50 years understanding all these things, and they're using that knowledge to see the system. But in this case, we're able to build a model that understands these things and can do it at scale easily. So, and all these things you can do yourself on Spark clusters in the cloud. You can set it up on your local, just reduce the data sets and stuff like that. So I think that's it. If you have any questions or comments, just follow us on our website. Drop me a mail. Yeah, and that's it. Just follow us. And much credit again goes to Neil Merchant, Rebecca Stilts. They worked a lot on this project, and a lot of all the things we're doing were based on the foundations that they laid. So we need to give all the credits to them on this. So I think that's it. Did I overrun my time? If you have any questions, just bring it on and let's talk a little bit. Thanks, everyone. Hope you're able to like learn one or two things from this.
Yeah, thank you, Charles. This was really an exciting session. Such outpouring of love and knowledge makes me giddy with delight. It gladdens my heart to see the contributions of our interns on YouTube and on Zoom. Alaji Dot and Happiness James, interns on our program, suggested that we can use this model in crime detection and carbon impersonation. Also, Alaji Kodri also accentuated that this same model can be used in the banking sector. I have some questions here for you. The first on my list is from Jaru. I do not understand what longest common sequence is. Can you explain?
I think if I recall correctly, it's talking about a SCQ. So it's basically it's syntax and scalar. So basically what we're trying to do is to just create a list. It's like your array list, but it maintains a sequential order. So I mean, I can follow up with you on the group channel as well. I mean, on the Slack as well. But basically, if you're interested in Slack, which is, I mean, in Scala, I'm mixing it up for Slack. If you're interested in Scala, those are kind of things that you do. So I'll say start up with Python. It's called functional programming. The reason we used it was like it's a lot more easier to like do a lot of things with it in a distributed environment, especially those who will be doing data engineering and moving data around and stuff like that. A lot of people use it in Facebook, LinkedIn. I know LinkedIn for sure they do a lot of Scala, and Twitter. They open sourced a lot of projects around Scala. So it's one of the things you want to know down the road, but maybe start with Python now. But once you're trying to go beyond just one computer and you're trying to leverage multiple clusters, multiple nodes in a cluster, I think that's where a language like Scala excels. And a lot of all this, it's an evolution from Java. So a lot of all the syntax is similar to what you see in Java, but with some slight nuances to it. So it's something that you can pick up at your free time and you enjoy it.
All right, thank you, Charles. Jaru again wants to know if the model can be used in crime detection.
Absolutely, you can do that. So the whole idea is like you want to know if something is. So I mean, I keep talking about digital trail and signature. So you can basically group things together because all you're trying to do in crime detection is to see like, okay, most of the time people who commit crime claim they're not the person that did it, and you want to be able to triangulate and put them in a location. So if you have all these indicators or markers that basically represent the signature about a particular criminal in a location, and you're able to like tie it together, I think that helps a lot. And there's certainly a use case for that in crime analytics and things like that.
Right, thank you, Charles. Mayowa says, hi, Charles. During the partitioning of the data sets into different chunks in Apache Spark, do you define your clusters, or is it an automatic process?
Yeah, that's a very good question. So one of the things you do is like you want to be smart about it. A lot of all these things are not like there's no add and fast rules. What I showed you went through multiple iterations and lots of work to like get to the sweet spot. So it depends, I would say, on your data sets and choosing your partition functions wisely. So what you want to do is like you want to leverage all the calls of your distributed nodes. So let's say you have a 10 node cluster and you have a lot of people, and you want to choose your partitions wisely so that everything is evenly distributed. When I say evenly, so on a 10 node cluster, you want to have close to 10% of the data set on each of the nodes. So if you don't choose your partition function wisely, you may have like 50% on a particular node and maybe 5% on another node and maybe 10% or 15% on another node. So that becomes very inefficient because the nodes with like 50% of the data is going to be doing a lot. And the other nodes are just going to be there idling around and stuff like that. So you want to be able to like, you do a lot of data preparation. You understand the distribution of your record sets by their attributes. And based on that, you can now decide, okay, I'm going to use this attribute. So let's say we're using cities. And you know, like, okay, in this country, there are like 30 cities. So you want to split your data sets so that each node gets a chunk of the data that represents a normal or almost even distribution. So in that case, you can decide to use, okay, I'll use the cities as the attributes to like split or partition my data sets and stuff like that. And if you find out that that's not efficient, then maybe you can try to identify or devise a very efficient partition function. The whole idea of partitioning the data is like, we don't want to search through the entire data set at once. It increases the quadratic complexity of the problem, because if you're comparing a billion records, so a billion times, you can now imagine how crazy that will be. So, or one of the smart things people do is to like partition the data sets into small chunks so that if you're comparing things, worst case, you're comparing a few hundreds or few thousands and stuff like that. So that's where choosing your partition functions efficiently really matters.
Right, thank you so much, Charles. Akinuye Cornelius from YouTube is asking, the Spark tool is very cool, but can we install it as another feature in our normal Apache server?
Can you come again on that question, please?
The Spark tool is very cool, but can we install it as another feature in our Apache server?
I'm trying to understand that question, but I'll answer as best as I could. So you can go check out the Spark. It's called, just Google Apache Spark. So you can run it in a distributed mode and you can run it in a local mode. So you can basically grab the example of what I did there and just subset the data and run it on your local computer. Or if you have some record sets that you can pick up or that you've curated that your company works with, you can take it up and just run it on the cluster as well. So, but the whole idea of this is you want to be able to like run it at scale in production, and that's where we leverage a cloud. And if you're very efficient, you can basically run this at almost close to zero cost on the cloud, which is something that we can talk about at some point once you guys get into like the data engineering part of this, where you want to be able to like spin up the nodes in the cloud, run your compute and get a result and shut it down. So it's not like it's not a dedicated resource, it's a resource on demand. So whenever you need that resource, you bootstrap the infrastructure. You have your data sitting in the storage, you run it through the compute nodes, it runs the computation. Sometimes if your data set is not much, you can just, because you're doing parallel computing, you're not limited by by each node. It's a cluster, so you can just basically have, if you have maybe 10 nodes, you can have 10x performance compared to running it on your local and just your own CPU core. So once you run it on that 10 nodes cluster, you get a result out, you write it. And once you write a result to a bucket, you shut down the cluster. So that's the advantage of doing things on the cloud, which basically allows you to like quickly experiment, see your results, and you're not committing to like owning all this infrastructure. It's just as needed, it's on demand and stuff like that. So I think Google Cloud, if I can give a plug for them, they give out like free $300 credits. So depending on how you use that, if you sign up for Google Cloud, I think you can get like a free $300 credits to just test run all these things. Give Apache Spark a kick and stuff like that. They have a managed service called Dataproc, which you can, it's basically a managed Spark cluster. So you're not going to have to be the one installing it. You just bootstrap it and you have all your nodes and all your cluster, and you can basically, you can run all the things you need to run on it. But I'll say before you do that, just try to read up on Apache Spark, understand the whole concept of what Spark is all about and what distributed computing on Spark is all about. And once you have a good understanding and solid grasp of that, then you can just sign up on Google Cloud. They give you a free $300 credit to like test run things, and you can give it a spin and see the results.
Right. Umar Sheo says, how is Spark different from Hadoop? Can Hadoop be used for partitioning data sets the same way Spark is used?
That's a very good question. So Hadoop, so if you've been in this space for a while, it's basically like an evolution. So Hadoop was the way things were done before. So the original problem all these things we're trying to solve is it's basically you can have a database to try to solve this kind of problems, but the problem with that is like you're limited to the bandwidth. I think the 64-bit conduit that your PC have. So just it's kind of like you have a door, and even though you have a lot of space, so if you imagine you have a big house and you have a lot of space in that house, you have lots of memories and lots of things in it, but you have just one door, and you're trying to get in like 100,000 people in that house. Everybody will have to queue to enter through that door to get inside the house. And that's the limitation that a single node computer tries to solve. Then Hadoop came along and with Doug Cottons, I met him a few times, very nice guy. So they developed Hadoop, and with Hadoop, you have like a way to gang up all these computers. So just imagine the house again. Instead of having one door, you now have like 10 doors to like enter the house, and it becomes a lot more faster, so people can just queue in on all the 5 doors and come in and out and everything. So you can get a lot more done. You can get people inside the house if you have an event going on and stuff like that. So Hadoop solved that very well. But the thing about Hadoop is like it's based a lot more on the file system. So it's a distributed file system. So once you have your Hadoop cluster configured, if you drop a file on a particular node, you can basically see it on the other node. So, and it's very good. They still use up to now on the Spark clusters as well. And it's centered around the concept of map reduce, which you map all your data, you push it all to the other nodes, you compute on it, you aggregate it back, and you bring it to your main cluster, and that's how you see the results. But the advantage of Spark is like it it does a lot of things in memory. So instead of depending a lot on the file system, a lot of Spark computations is in memory, which gives us a lot more a faster performance, like several. I forgot exactly what the metric is, but it's over 10x of what you get from Hadoop with traditional map reduce. So with Apache Spark, you get a lot more things done. You use the RDD to represent your data across the different nodes, and it basically handles a lot of things under the hood for you. And the RDD, you can load it, you can you can execute or you can execute all the transformation you need to do in one shot, and it's a lot more efficient in terms of how it does things, and the speed and performance in Spark is a lot more than Hadoop. So that's why a lot of people are tending towards Spark right now, but there's still a lot of things to do on the Hadoop side as well. There are a lot of legacy projects that are running in Hadoop, but Spark is really used a lot in a lot of new projects right now, and all these things. The evolution is just very fast because I can still remember when Hadoop was the main thing in around 2012 up to 2016 or so. But I think Spark is a lot more a lot of projects have been implemented in Spark, and Google has another product called Data Flow with Apache Flink also there as well. So you can read up on all these things. Distributed computing is a big problem that people are trying to solve, and they're devising smart ways of doing it all the time.
All right, thank you, Charles, for
Yeah.
that clarity. This is a very interesting question from Ali Ukodri. So I was wondering what role can SQL play in all of this? How do data storytellers also benefit from understanding the Bayesian model on Apache?
Yeah, sure. So that's an equally very good question. So I think I can read that question as well. So SQL, maybe you need it in your data preparation step where you're trying to understand your data and see what's going on there. You subsample it. But the problem and limitation of SQL is like it's based on the single node architecture where whenever you run your SQL query, it's executing on a particular node in a cluster, and it's not built to run on a distributed cluster. It's highly structured. So that means you have your data and your table all like all the relationships and all the relationship integrities are in place and stuff like that. So, but when you're solving all these like large scale problem, you need to relax all those constraints, like I love all those joins and foreign keys and stuff like that. They're like for the SQL world, but once you move to they call this NoSQL, the NoSQL world, you allow the data to be in free form, so it allows you to quickly like execute a lot of all the things you're doing. So a knowledge of SQL will help, but I think you need to think out of the box, and this is beyond SQL. But I mean, in transactional stuff like relational database, I mean, in things like in the financial world where you need to enforce transaction integrity and things like that, the SQL might be a good way to go. But once you start hitting all these large scale problems and stuff like that, I think SQL becomes more of a constraint than a value add. So I think in that case, you probably need to like understand a little bit of all these things. But it's a good foundation. I started from SQL as well, so there's nothing wrong in knowing it and understanding how all those work, especially if you're building web applications and stuff like that. So the other question was like the naive-Bayes approach and how you can use it as visual storytelling. So yeah, what I just did right now is partially visual storytelling. Basically doing all these things, and we did a lot of research on this, a lot of iteration, lots of long nights, and summarizing it and making it into presentations. We did this presentation at the Spark Summit earlier this year, last month rather. There's a lot of opportunities like that for people who want to like talk about all these things, which is like you understand the problems, you present it in layman's time so that people can understand what you're trying to solve, and and basically get a lot more people interested in it. So there's a lot of room, obviously, for visual storytellers, and we're working with a lot of people. We have some interns with us doing a lot of that right now, where they try to like understand the problem we're trying to solve and create a visual picture of it for people to understand.
Thank you, Charles. This is a question about the application of the model. So Oluwaseyi Akinkumi is asking, how can this model be applied in traffic control? And what are some of the important attributes or features to consider when trying to obtain the data needed?
Yeah, I mean, that's a very good question. So, I mean, I'll have to think about that as well. And it's a kind of problem that I'll be interested in solving. So if you can hit me up offline about that, maybe we can talk a little bit more about it as well. So you just need to imagine the use case and what you're trying to solve and how do you represent the problem. So let's say what causes traffic? Why do you have traffic? Traffic is when you have a buildup of commuters trying to go from point A to B and they're stuck in a location. So you now need to start dissecting the problems. Like, okay, how do you track if the traffic is going slow at a location? Do you triangulate and try to measure the cell phone signal so that you can work with telco companies? So, okay, if you're like at a particular location and you have a lot of people trying to hit the network or they have a lot of drop calls, maybe there's a cluster of traffic around that place. Or do you put a sensor out there that basically measures the the emission and try to say, okay, is there like a lot of CO2 from like from the exhaust of the cars and stuff like that. So you have to have a metrics that you use like measure a lot of all these things and try to a particular user. So for traffic though, I don't think this would be like an exact fit. because traffic, you're not thinking about the individuals, you're thinking about a cluster. Like, okay, how many cars are here? What's the throughput of this particular location, and things like that. So there might be ways to like leverage a lot. I mean, some of the things we've done around this, like now, if you can just basically identify if there's a congestion in a particular place, but when you're solving that problem, you're not trying to identify who's in the traffic and things like that. But maybe it's something to evolve. I mean, to think about too. If you have, let's say, you're running a logistic company where you're distributing and moving things around, and you have a lot of vehicles on the road, and you want to track where your users are or try to guide them through roads to avoid and stuff like that. Maybe we can see how we can leverage this and stuff like that. But for traffic, I think it's a lot more around identifying where the cluster of commuters are, and now you can basically create an alternate route or predict how long that traffic is going to last.
Yeah, thank you, Charles. So we have another question from Ariel, an intern. So talking about similarities measures, please can we use the cosine similarity as well, aside of all similarities measure we've seen during the presentation? If yes, what can be its advantage or disadvantage?
Oh yeah, that's a very good question. A very good question. I'm intrigued. So basically, the different similarity measures, like I said, a similarity measure is basically a way for you to measure the distance between two attributes. So I mean, the example I used earlier is like, if you want to know how close, if I want to know how close we are, we do like the distance similarity measure. Where do you live? Where do I live? If you live a few blocks away, a few miles away, or thousands of miles away, I can measure how close this two people are. So same thing with like the cosine similarity measure, where it's used a lot in like in recommendation engines and stuff like that, where in vectorized words, you want to see if two words are similar or they're synonyms. That's where you use the cosine similarity measure. So if you're doing things around like, let's say, document understanding with AI and classification of documents into like different topics buckets, cosine similarity measure plays a big role in that. So it could be one of the attributes you have. It's not what I presented is not like, okay, these are what you need to use. The different similarity measure techniques depending on what you're trying to study, what you're trying to observe. Say, for instance, Levenstein similarity measure may not work on localized name. So let's say someone like my last name, Aditloye, which is, it's more of a Nigerian last name. Levenstein will fail on that. So you can come up with like your own similarity measure of what you use to like measure the distance between the names based on the location, state of origin, address, first name, last name, and stuff like that. So a lot of all those things, it's not like hard and fast rule. We can test out things, and that's the beauty of all these things. You go through several steps before you arrive at your final results, which is you do a lot of experiments. There are a lot of things that we considered that never worked, and there are a lot of things that we considered and they worked, and you just add it to your toolbox and things like that. So cosine similarity measure is a way to do things. You can look into it, and in your use case, that might be a good way to go around things. So yeah.
Yeah, thank you, Charles. And this will be the last question. I'll be merging two questions from two different learners.
Sure.
So Shafiu Abdusalam, he wants to know the optimum RAM and processor size recommended for data engineering. And also T. Bajon, let me see. Yeah, that's all from Shafi Abdusalam. The optimum RAM and processor size recommended for data engineering. That's the last question.
Yeah. So in terms of the RAM, I'll say just get something very decent. Over time, one thing I do is like, as you guys progress in this, you can start looking at leveraging the cloud. You get a lot of bandwidth, you get a lot of opportunities to like run things at scale in the cloud. So, but for now, just whatever you can get. I won't put any hard and fast rule to it, but anything from maybe 16 gig of RAM and a decent CPU should do it, like just that. But a lot of all these problems are beyond what you can just solve on your computer. You need to like scale it out and do things with like a bigger compute resource. So over time, you can start leveraging the cloud, which that will be the ultimate destination for those who intend to go deep into this and get going and be a lot more advanced with all these things. So that's what I would recommend.
Thank you, Charles. I've seen some questions regarding the video. Yes, this video will be recorded, and you can always this video will be recorded and you can always access it on YouTube. So quickly, a quick synoptic of what was discussed. The problem of deduplicating data was brought to fore. How data occur in multiple places and multiple data sources but belong to the same entity. We learned about the spatial temporal data and the various use cases, especially community health, and how this model can be developed to tracing people that have contacted or had contact with people with someone that was infected with COVID. We also learned about the current method and solutions for deduplicating data such as brute force, logistic regression, and unsupervised learning, not to mention how string comparison for fuzzy matching dataset is used. I don't know what your favorite approach is, but mine is the Levenstein approach, and I'm completely in love with this approach. Charles also discussed in depth on how to perform distributed probabilistic record linkage on Apache Spark using a Bayesian generative model, which teaches how an observed data can be produced based on prior information. He also did a live demo. Thank you so much, Charles. It looks like we've covered all the questions. Is there anything you'd like to say before a final wrap up?
I think I just encourage guys to keep improving yourself. Rome was not built in a day, but as long as you're making progress and you're adding value, things will keep getting better. So I would say just keep pushing yourself. There's a lot to do. There's a lot more problems to solve out there, and there are very few people to solve it. So the whole idea of doing this is to get people excited, get them fired up, and see how we can work with you, build something great. And the whole idea is to build something big enough beyond you, so you can see all the different kinds of problems and use cases and domains of problems that all these things touch and apply to. So there's always a position for everyone out there willing to just go beyond the normal day-to-day mundane stuff. It's tough initially, but once you get a good grasp of this, there's a lot to do. So just keep at it. We're looking forward to those who are working out on all these cohorts and all these problems that you guys are solving. And I look forward to, I'm really excited, and I look forward to working with some of you in the nearest future and for a much longer time to come. So thanks a lot for your time, and I really appreciate this. Yeah, thank you.
Awesome. Thanks again, Charles. Thank you, everyone. We appreciate you for being here. Thanks again for joining us today, and we'll see you another time. Bye.